Hi. Okay, so this is a fun topic. It's particularly fun in the classroom because we can do a fun lab activity with it. And I don't know that that will be happening. Um, we're going to look at Dalton's law of partial pressure and collecting gas over water. All right, very random. Um, so all these gas laws, right? We learned the gas laws. This is more of an application of the gas laws. It's a particular type of lab activity that is done. Why would you do this? Maybe to identify the type of gas that might be present, to calculate the partial pressure of the gas, and then to you can determine percentages of gas is present in a mixture. So there's applications that are beyond our skills at this given moment, but let's just look at the basics for us. All right, so we'll start with Dalton's law of partial pressure, and it couldn't be any easier than this, because what Dalton proposes is that whenever you have a mixture of gases, the total pressure is simply equal to the pressure of the individual gases added together. It does not matter that's all that matters. It's just the right. If I have a total pressure of 700 mmHg, and I know that one gas has a pressure of 300 millimeters mercury, then the other gas has a pressure of 250 millimeters mercury, and there's only one more gas, then I can determine that pressure 3 of the third gas must be 150 millimeters mercury. Okay, because if the sum of the individual pressures of each gas is equal to the total pressure of all of the gases. Can't be any simpler than that. Now let's apply that to collecting gas over water. So what would this setup look like? We could have an experiment here, all right? Kind of like this. Here's our flask. And let's say that in this flask, we have some hydrochloric acid, all right? We've got some hydrochloric acid floating around in there. And then we dangle from here a little cage, and that cage has some metal in it, all right? And in that metal there, we need to get a better color, will be zinc metal, all right? And when those react, we will get hydrogen gas and zinc 2 chloride will be aqueous. So let's balance that equation. Notice here is the gas. Well, what is that going to do? It's going to immediately start bubbling up, right? Okay, well, remember part of our title was collecting gas over water. So if prior to allowing the zinc to come in contact with the hydrochloric acid, I set it up so that there was a rubber tube here, all right? So this is my rubber tube. It's a gas collection tube, all right? And I may have to erase and redraw because I'm not sure, right? But my gas will be confined to this tube. Now, what I will also have is a big sample of water here, right? I'm going to have a big, I can't think of the word I want to use, container, and I'm going to have water in this container. And the other thing I'm going to do is I'm going to get, if we were in our lab at school, we would use an inverted graduated cylinder. If we had more professional tools, we would use something called an eudiometer or a gas burette, okay? But let me get this pressure 3 out of our way. We would take a graduated cylinder, and I would have you fill it up with water, and I would tell you to turn it upside down real quick. And what we would end up with is this graduated cylinder here, okay? It's upside down, and it's filled completely full of water. All right? Okay. Now remember, we're going to collect this gas. So let's go back to our gas collection tube. It's got really long. And we would put it all the way in here and into the inverted cylinder, such that our hydrogen gas that we collected by our displacement reaction is going to come into this tube, right? So it's going to go all along here, and it's going to settle up here. And what will happen is it will do something called, you know this word, displacing the water. So where the water in the cylinder was, let me clean that up, make that a little bit neater. Where the water in the cylinder was completely full, it will now not be as full, okay? It's now going to look more like this. We still have the gas coming in. The gas has collected up here, all right? The water has been pushed down due to the pressure of that gas, okay? So what you can see right here is that we have literally collected the gas over the water, right? It's sitting over the water. Well, now I need you to think about something. If we were to look more closely, so let's take a macroscopic look at what's going on in this inverted cylinder, right? Which has some water here. And it's got our hydrogen gas particles floating around. Well, what is some of this water going to do? What does water do as it sits there by itself in any given situation? Some of it evaporates, right? So we end up with not only the gas we collected, but we also have water vapor, which itself is a gas. And because, oops, let me move this, because it is a gas, it has a pressure. So what we have is a situation where we have a mixture of gases, like in the beginning of this video where Dalton talked about, well, if we have a mixture of gases, then the total pressure is equal to the pressure of each of the individual gases. So the pressure inside of here, actually that's too big of a thing. The pressure inside of here sitting on top of the water where we collected the gas on top of the water, the pressure total here is equal to not only the pressure of the gas we collected, but the pressure of the water vapor. That has also, right here's our water vapor up there. This value is temp dependent, right? The amount of water vapor that is in equilibrium that evaporates from the sample of water depends on the temperature of that water. The greater the temperature, the more water vapor you'll have, the greater the vapor pressure. So, and this is often given, or you can easily look it up, okay? It is easily looked up. There are reference forms for all of that data. We, however, are concerned with the hydrogen, right? Because we collected the hydrogen gas over the water. The total pressure, all right, it's the last thing we need to talk about. This total pressure. Well, the total pressure here, right, is equal to the atmospheric pressure that is pushing down on this water in this basin. That's what I wanted to call it, a basin of water. The atmosphere, which itself is a mixture of gases, is pushing down on this basin. And this in turn, it's hard to draw in here, right? Let's see what color might be good. No. I'm sorry, I'm just looking for a good color. This in turn is pushing up, right? We're pushing up with a pressure here, as this is pushing down with a pressure here. So when these water levels, technically these water levels in this basin, right? When these water levels are equal, then the total pressure is equal to the atmospheric pressure. All right, if you don't understand, I can go over that again. But the total pressure is equal to the atmospheric pressure. So let's look at our problem. We've got a problem here. Let's see, different color. We've got 193 milliliters of oxygen gas. So we're concerned with the oxygen collected over water on a day when the atmospheric pressure, so that's our total pressure, is equal to 762 millimeters mercury. The temperature of the water, that's 23.0 degrees Celsius. The reason we need to know that, for one, is to know the vapor pressure at that temperature, right? So let's go ahead and add 273. I should have done that in my head. That's 296 kelvins. How many grams of oxygen? Okay, all right. So what I have here is a volume, a pressure, a temperature. I need grams. I must need to solve for moles. And then I can convert my moles to grams. This is a volume. It's in 193 milliliters. I see that I will need to use my ideal gas law. So I must convert my milliliters to liters, and that's 0.193 liters. Okay. So let's go PV equals nRT. Hold on. Notice that this is the total pressure, and we need the number of moles of oxygen. Therefore, our pressure must be the pressure of oxygen. But what we have is a total pressure. And whenever we collect gas over water, whenever you see collected over water, that means that you have a partial pressure problem. All right? So we need to take our total pressure. I'm going to write down here, turn it to maybe a red. P total equals, well, it equals the oxygen gas that was collected. And remember, it was collected over water. So we have some water vapor pressure. All right? So the P total here is 762 mmHg. We need the pressure of the oxygen, and we're given the pressure of the water vapor at the given temperature, that is 21.1. All right, so the pressure of our oxygen will be the difference in those two, and that will be 740.9 millimeters mercury. Okay, so let's plug in our pressure to our ideal gas law and solve for number of moles. 740.9 mmHg. Our volume in liters is 0.193 liters. We're solving for moles of oxygen. R is 62.4 liters mmHg, moles kelvins, and our temperature is 296 kelvins. We're going to need to bring all of this over here so that we can solve for a number of moles of gas. So it will be 62.4. Don't be lazy. Okay, let's check our units. Part of our learning, mmHgs are gone. Liters are gone. Kelvins are gone. We're solving for moles. We're getting moles. We're solving for moles. Good. Okay. Let's just do the math now. 740.9 times 0.193 equals, divided by parentheses, 62.4 times 296 close parentheses equals, I've got, whoa, got a very small number of moles of oxygen. So small, I'll probably try it again to make sure that I didn't make a mistake, because I got 7.74 times 10 to the negative third moles of oxygen. Let me try that one more time. Yeah, that's a pretty small number. Yeah, and then that number on bottom is pretty big. Okay, yeah, and that's moles of oxygen. The question asked for grams of oxygen, so we know that 1 mole of O2 is equal to 32.00 grams, and times 32 equals, I've got 0.2, looking at my sig figs, looks like we have 3, so I'll go 4.8 grams of O2. Whenever you see collecting gas over water, you need to simply make sure that you take the time to subtract the partial pressure of the water from the total pressure so that you can get the pressure of the gas you're concerned with. All right, right on.